Hi, welcome to this ISPD presentation entitled Design Flow Parameter Optimization with Multi-Phase Positive Non-Deterministic Tuning. I'm Matt Ziegler. My co-authors are Lakshmi, Reddy, and Rob Franch, and we're all from IBM T.J. Watson Research Center. Aggressive PPA that we're targeting in today's chip products often push CAD tools to the limit. We're using design flow tuning routinely to get near optimal results, but this can be challenging in non-deterministic CAD tool environments. For example, CAD tools given the exact same inputs can often return different results, commonly due to multi-threading and algorithm implementations. And this is typically thought as an unwanted behavior, but in this talk, we'll talk about how we can use this to actually improve our tuning results using a technique called positive non-deterministic tuning, or PNT. PNT relies on two key principles. The first one we'll call forking. In this case, we're going to take a standard tuning framework as we see here, which has parallel scenario submissions and iterative refinement. This is an online tuning technique, but this is a very common framework. Really, I think for any online approach where you're going to need some sort of parallel iterative framework, we're going to try a simple approach to modify this technique by introducing what we call forking. In this case, we're going to intercept each scenario, fork it a number of times, and then select the best solution and return that to the machine learning algorithm. In a way, we haven't really modified the underlying algorithm itself, although you could actually make even a more complex algorithm by having the forking inherently known to the algorithm itself. We're trying to simplify things today. The second technique is called multi-phase tuning. In this case, we're going to run multiple passes through the flow, but at each pass, we're going to save out information, what we'll call a seed for the next pass. And so in the next pass, we can modify then the parameters that we tune and start with a seed. So in a way, we're eliciting a good outlier, and then we're able to restart at that point and try to elicit even more positive non-determinism and tune with new parameters. We have three types of seeds. One's called a checkpoint that saves out the complete database, everything including the standard cells and CTS network. We have another approach called preplace, which only saves the CTS networks, registers and clock buffering. The third approach just is called attractions, and it just saves the registers and allows the tool to actually override the attractions and gives it the most freedom. So there's a spectrum of flexibility versus runtime savings that these techniques approach or provide. Now we're going to compare against 6 different flows. We have our default. If we ran the CAD tool 150 times in parallel, and basically this will show us how much non-determinism will give you alone. We have a stable setting where we run it in a higher runtime deterministic mode. We run against our state-of-the-art tuner STS. This is what we use to tune our IBM servers for the last 10 years. So it's a good parameter tuning reference. And then we compare against the 3 different PNT modes we described previously. Now, overall, when we run this against 5 industrial macros, we see all PNT flows outperform our current tuning approach. We see that the attraction mode generally performs the best in terms of QOR. The preplace mode has the best in terms of congestion. And the checkpoint mode, although the QOR is not quite as good as the other modes, is actually faster than the other modes because it doesn't have to run the second phase of the flow the entire way. It can reboot at the checkpoint. So another result is that after we perform the tuning, and if we're going to run the best solution numerous times, our PNT2 approaches are actually more repeatable. Effectively, this makes sense because the seeds introduce some amount of repeatability. And so actually, even though we use non-determinism to get a good result, what we wind up as is a more stable solution compared to running the flow from scratch. We have a number of other results in the paper. Please check it out to get more details, and also check out our longer slides and video. And to summarize, we've addressed this problem of non-deterministic CAD tools in the design flow tuning using an approach called positive non-deterministic tuning, or PNT. We showed that PNT can outperform existing industrial design approaches. And maybe to summarize, if you can't avoid non-determinism, perhaps leverage it to get a better design. It might even suggest that we should add more non-determinism when needed to elicit even better outliers. So with that, thank you and take care.